that we have learned about force, let's discuss another concept called electric field. This was introduced by Faraday. This is used to explain the interaction between two charges placed at a distance. Now let's define electric field. Electric field E at a point is defined as the electric force experienced by a positive test charge Q0 placed at the point divided by the magnitude of the test charge. Mathematically, it can be written as E equal to F by Q0. Note here that the electric field is a vector quantity and will have the same direction as the electric force F. The electric field is due to the external charge and not due to the test charge. It has the unit Newton per coulomb. Okay, so why the test charge Q0 should be infinitesimally small? Let's consider both the cases to understand this. Consider the figure A, where the uniformly charged metallic sphere with charge Q is placed and the test charge Q0 is very infinitesimally small. It means that the charge density per unit area is same around A, B, C, D in the sphere Q. And the test charge Q0 measures the force F without disturbing the charge distribution on the sphere. Now consider the figure B. Here the test charge Q0 is considered to be of charge almost equal to charge Q. In this case, the presence of this test charge modifies the surface charge density of Q. As a result, the electric force experienced by Q0 will also change from F to F dash. That is, the force in the presence of test charge is different from that in its absence. But without Q0, the force cannot be measured. We see that if Q0 is infinitesimally small in comparison to the Q, the charge distribution on the sphere will be minimally affected and the results of the measurement will have a value very close to the true value. That's why the test charge should be infinitesimally small. Okay, now let's see the mathematics part. Let's consider that to be a point charge Q, a test charge Q0 is placed at a distance r from Q, then the force experienced by the test charge is given by F, k Q0 Q by r square, where the unit vector r denotes the direction. So now we know the force. What was the electric field? It is defined as force per unit area, hence E is equal to k Q by r square with the unit vector r denoting the same direction. Similarly, the force on a charge Q in an electric field E can be denoted as F is equal to QU. These are just the mathematics which will be required while solving the problems. To get more clarity, I have added everything in the same slide. We saw the electric field for a point charge. What if there are many charges? The principle of superposition applies to electric field also. If there are a number of charges Q1, Q2, Q3, the corresponding fields at a point P are here given below, E1, E2 and E3. The total field P due to all this charge is the vector sum of all the fields. Mathematically, we can represent using the summation formula. Here, Ri is the distance between P and the charge Qi, and vector Ri is the unit vector directed from charge Qi to P.